Section: Introduction. In this section, we explore the concept of in-context learning, ICL, and its applications in various tasks. While the exact workings of ICL are not fully understood, it has gained popularity in academic and industry settings due to its simplicity, low computational requirements, and the ability to use a single model for multiple tasks. Most research has focused on short context models, limiting the number of examples that can be used. However, advancements in adapting language models to longer contexts have made in-context learning over large datasets a viable alternative to fine-tuning. We conducted a detailed study on long context in-context learning, examining different approaches such as prompting the base model, retrieving examples for each test case, comparing to fine-tuning, and using models trained for longer contexts. Our findings show that as the number of examples used in context increases significantly, the behavior of ICL changes. It becomes less dependent on the order of examples and the benefits of retrieval decrease, allowing for the reuse of a single set of examples encoded once through the model. We discovered that grouping examples with the same label significantly impacts the effectiveness of long context ICL. The success of long context ICL is attributed more to retrieving relevant examples rather than continuously refining decision boundaries during encoding. Our research enhances the understanding of in-context learning and suggests that in certain scenarios, long context ICL can be a robust alternative to retrieval and fine-tuning methods. Moving on to the experimental setup, we describe the common setup for both our ICL and fine-tuning experiments. We analyze 5 classification datasets: TREC, TREC Fine, NLU, Banking 77, and Clinic 150. Our comparison of ICL performance includes various adaptations of Llama 2 to 7B for long contexts, such as Llama 2 to 32K and Llama 2 to 80K. Additionally, we consider Mistral 7BV0.2 to ensure our observations are not specific to the Llama series. To ensure valid outputs, we employ constrained decoding for each dataset, allowing only valid labels to be generated. Evaluation is done by subsampling 250 examples from the test set of each dataset and measuring accuracy and macro F1 scores. We primarily report accuracy for readability, as the trends for both metrics align closely. Section Summary. In this section, we delve into the realm of in-context learning, ICL, where large language models can excel in various tasks with just a few examples provided in context. We explore the performance of long context ICL, finding that as the number of demonstrations in context increases significantly, the behavior of ICL shifts, becoming less sensitive to example order and benefiting more from retrieval over using a random set of demonstrations. Our study reveals that long context ICL is strongly influenced by grouping examples of the same label and is effective not due to continual refinement of a decision boundary during encoding, but rather due to retrieval from more relevant examples. Section: Long context ICL. In this section, we explore 3 common methods for utilizing a large dataset in our in-context learning, ICL, experiments. Firstly, we can randomly sample a fixed subset of data for each in-context example. Secondly, we can retrieve relevant examples for each test set example using a BM25 retriever. Lastly, we can fine-tune our model on the full dataset. When it comes to random sampling in ICL, we conduct 10 random shuffles of the training dataset and average the results across these shuffles. We then draw the first n examples from each shuffle. This method allows us to encode demonstrations once and reuse them for all inference examples. In the retrieval ICL approach, we use a BM25 retriever to fetch the most relevant examples for each test set example by comparing the test input text to the full demonstration texts. If we need more examples than retrieved, we randomly sample additional ones until we reach the desired number. This method is more computationally intensive than random sampling but has shown to significantly improve test accuracy in certain scenarios. For fine-tuning, we use the Llama 2 to 7B model with a classification head on varying amounts of data from each dataset. We initialize the classification head using the parameters of the pre-trained language modeling head for better fine-tuning. Scaling up ICL to include more examples has shown to yield impressive results, with accuracy gains of up to 50.8 points when moving from 10 to 1000 demonstrations. In the long context scenario, the importance of carefully selecting in-context examples diminishes. Comparing retrieval ICL with random sampling, retrieving relevant examples for each test set example performs much better, even when the order of retrieved examples is shuffled. However, the performance improvement diminishes as more examples are added. In contrast, using a single randomly selected set of demonstrations in the long context regime is more feasible and only incurs a slight performance penalty. When comparing with fine-tuning, in-context learning with hundreds or thousands of examples proves to be effective. However, fine-tuning is more data-hungry and may have reduced inference time costs. In general, in-context learning outperforms fine-tuning when a small set of examples is available, except for specific datasets where fine-tuning excels at higher numbers of examples. Section Summary. In this section, we explore 3 common methods for in-context learning, ICL, using a large dataset, random sampling, retrieval of relevant examples, and fine-tuning on the full dataset. We find that retrieving relevant examples for each test set example outperforms using a randomly selected subset, especially in the short context regime, but the advantage diminishes with additional examples. While in-context learning with hundreds or thousands of examples is effective, parameter-efficient fine-tuning, PEFT, may be more data-hungry and have higher upfront costs, yet it allows for reduced inference time costs. Section. Properties of long context ICL. In this section, we compare the properties of long context ICL with those of short context ICL. We also explore using ICL as a testbed for long context models in the appendix. We investigate whether using the entire context is the best approach. Previous studies suggested that providing additional input for simple tasks could sometimes decrease performance. However, we noticed a consistent improvement in performance across almost all datasets. Even when the performance levels off, there are only minor fluctuations, and no significant drop in performance with more examples. While using the full context window can be computationally expensive and may not be essential for achieving high performance on these datasets, it does not seem to harm performance. The extra cost of more input is minimal because the key value pairs can be cached and reused for test samples. We also look into the sensitivity to the order of examples. Previous research has shown that many models are sensitive to the order of examples in the context. We measure the percentage of predictions that change when the input is shuffled and find that while there is some sensitivity at all context lengths, this effect decreases significantly with more context. In all datasets, reshuffling in a 1000-shot ICL results in fewer label changes compared to reshuffling in a 10-shot ICL. Furthermore, we examine label sorting, where examples with the same label are grouped together. At small example numbers, this has little impact, similar to random sorting. However, as the number of examples increases, label sorting significantly affects performance. This indicates that contextualizing examples with different labels is crucial for performance, and this contextualization is most effective over short distances in the context window. To understand why long context ICL is beneficial, we study a modified attention pattern where demonstrations can only attend to a nearby block of demonstrations. The test example can still attend to all demonstrations. By comparing this block attention to causal attention, we aim to determine if the improved performance is due to a more detailed task understanding from embedding many examples together or from seeing more relevant examples to attend to. Our results show that performance is not heavily dependent on how many other examples each demonstration is contextualized with. This suggests that the primary performance improvement from long context modeling comes from retrieving more relevant examples in context rather than learning better task boundaries. Section Summary. In this section, we compare the properties of long context ICL with short context ICL and explore the impact of using the entire context window. We observe that while using the full context window is computationally costly, it leads to monotonically increasing performance on various datasets without significantly lower performance at higher example counts. Additionally, we find that sensitivity to example order decreases with additional context length, and label sorting becomes more impactful as the number of examples grows, highlighting the importance of contextualizing examples with different labels within a relatively short distance in the context window. Section: Tasks where long context does not help. In this section, we identified tasks where having a long context doesn't always help. We noticed that some tasks either perform poorly with very few examples or actually do worse as the context length increases. These are important things to consider when studying language models, but for our analysis, we focused on tasks without these issues. We explored different ways to give language models more context. Some methods involve extending the context length during training, while others use techniques like retrieval-based attention or hierarchical merging of information. The two long context variations of the llama model we looked at involve fine-tuning to handle longer contexts. There are also methods for longer context in context learning, ICL, such as using parallel context windows or structured prompting. We also looked at how models handle long contexts. Some models struggle to effectively use the middle of the context window, while others may only work well with inputs shorter than their intended context length. However, these issues are less likely to affect our study. We also examined how models perform on tasks requiring reasoning over long dependency lengths, which is not a major concern in our work. We studied in-context learning for multi-class classification with models up to a context length of 4K. We found that smaller models tend to plateau in performance early on many tasks when retrieving examples. However, when these models are fine-tuned for longer contexts, they continue to improve. This suggests that the failure to utilize longer context effectively is not inherent to smaller models but rather a specific behavior influenced by the quality of examples. Our research also delves into the impact of various factors on in-context learning performance, such as ground truth labels and example selection. We discuss different modes of in-context learning, like learning tasks and retrieving tasks, and how the quality of examples can affect performance. Additionally, we explore the idea of in-context learning as a form of gradient descent and the concept of compressing demonstrations into a task vector. Furthermore, we compare in-context learning to traditional fine-tuning methods. Some studies show that models trained on few-shot learning can adapt well to new tasks, sometimes outperforming direct fine-tuning. Comparisons between in-context learning and fine-tuning reveal that the latter generally performs better with the same number of examples, both within and outside the original domain. However, the effectiveness of these methods can vary depending on the specific model and amount of data used.